Here is another example where we are going to find the critical numbers of the function and then find the absolute max and minimum values of this function using the closed interval method. So the function I'm going to do work on is this rational function, y equal p minus 1 divided by p squared minus 4. So I'm using p instead of x. The interval that I'm going to find the absolute max and min on is -1, 1. It's a closed interval. Okay, so the extreme value theorem will apply. So let's get started with this question. So the first thing I'm going to do in order to find the critical numbers is I am going to take the derivative of this function. It's going to require the quotient rule. Okay, so I have the bottom function times the derivative of the top function, which is just 1, minus, and now I'm going to take the derivative of the top function, which is p minus 1, and I'm going to multiply that by the derivative of the bottom function, which is just 2p. So this is just the quotient rule, and then I have the denominator, the bottom function squared. So I'm just going to clean this up a little bit. I get p squared minus 4 minus, and I'm going to distribute here. So I have a 2p squared minus 2p over p squared minus 4 squared. And then remember to distribute the negative. So over here I have p squared minus 4 minus 2p squared plus 2p. So that's where I'm distributing the negative. And then I end up with 2p squared minus 4, and these should both be squared. So y prime is negative p squared plus 2p minus 4 over p squared minus 4 squared. So that is the derivative of this function. And so if we want to find the critical numbers, I have to figure out for which values of p in the domain of my function y is the derivative undefined, and where is the derivative equal to 0. Okay, so those are the two things I have to look for. So if you take a look at this function, the first thing I'm going to point out is the domain is essentially the set of all values such that my function is defined. So the domain for this function is actually, let's just write this down. The domain of y is basically the set of all real numbers except for 2 and -2. Because when we have p is equal to 2 or -2, the denominator will be equal 0. So these numbers would not be considered critical numbers technically because they're not in the domain. Now, if you notice over here, my derivative will also be undefined at 2 and -2. Technically, those aren't critical numbers. So the only possible critical numbers would be points where my derivative is equal to 0. So when is the derivative equal to 0? So basically, the derivative is going to be equal to 0 whenever the numerator is equal to 0 and the denominator is not equal to 0. So we're going to actually look at this equation instead, and we're going to try to figure out when is p squared plus 2p minus 4 equal to 0, okay? And just remember that a quotient like a over b is equal to 0 if and only if the numerator is equal to 0. And also, obviously, b is not equal to 0, right? So that's the basic idea here. If you're trying to figure out where a quotient is equal to 0, focus in on the numerator. Okay, so in this case, this actually happens to be a quadratic equation with a equal -1, b equal 2, and c equal -4. So I'm just going to look at the discriminant, b squared minus 4ac, because I want to see is this actually going to be greater than or equal to 0. So I have 2 squared minus 4 times -1 times -4. And this gives me 4 minus 16, which is -12. So that's actually negative. So this has no real solutions, this quadratic equation. So my conclusion here is that there are no critical numbers. Okay, so that is actually part A, and that would be my conclusion for part A. So the second question is, can we find the absolute maximum and minimum values of the function on the given interval? Okay, so notice that this is a closed interval, and notice that since the domain of this function is all real numbers excluding 2 and negative 2, from section 2.5, we know that this function is continuous on, so this tells me it's continuous on all real numbers, except for 2 and negative 2. It's a rational function, so it's continuous on its domain. So that means that my rational function is y is continuous on this interval, -1 to 1. And the nice thing about that when we're looking for absolute max and min values is that we can apply the extreme value theorem. So recall the extreme value theorem was the theorem that told us that if the function is continuous on the closed interval, we are guaranteed that this function will attain the absolute maximum and minimum values. In fact, we can use this method called the closed interval method, and we just find the critical numbers. We already showed that there aren't any. And then we evaluate f at each critical number and also at the endpoints a and b of that interval. And then the largest value is going to be the absolute max. The smallest value is the absolute min. So I'm just going to apply this process. We already did step 1. So for part B, we first establish in step 1 of the closed interval method, there are no critical numbers, right? In step 2 of the closed interval method, we will plug in the endpoints. So f of -1, we're going to plug that into the function. So this gives me a -2 over a -3, which is 2/3. And I'm also going to plug in f of 1. And that is 1 minus 1 over 1 squared minus 4. So that's 0. So the closed interval method tells me that this is the absolute maximum on the interval -1, 1, and that this is the absolute minimum value on -1, 1. Okay. In order to convince ourselves, let's take a moment to graph this function and just see if this actually aligns with our results. So here you can see the graph of our function. And we're interested in the closed interval, -1, 1. So between the blue and the green line there. And you can see that the absolute, in that interval, the absolute minimum is indeed occurring at the point x equal 1, and it's 0. And you can also see that when x is -1, again, we have that the absolute maximum value is achieved, and it is, in fact, 2/3.